Welcome to Late Night History. Settle in. Let your shoulders drop away from your ears. Let the weight of the day pour out of your hands, out of your feet, down into the mattress and the floor and the ground below that, because tonight we are going to travel downward together, very slowly, into the warm and patient dark at the center of the world. There is no hurry here. Nothing we talk about tonight happens quickly. In fact, the whole story is a story about slowness, about a fire that has been burning for 4.5 billion years and will go on burning for billions more. Long after this night, long after every night either of us will ever know. So there is nothing to chase, nothing to catch up on. You can let the words wash over you like warm water and drift wherever they carry you. Let me begin with something strange and gentle, something happening to you right now, in this very moment. Whether you are lying in a bed or sinking into a chair or curled beneath a blanket in the quiet. Right now, as you breathe in and breathe out, tiny ghostly particles are passing through your body. Not a few of them. Not a handful. Roughly 1 million of them are streaming through every square centimetre of you every single second, through the back of your hand, through your chest as it rises and falls, through your closed eyes and the pillow beneath your head. They come up out of the ground beneath you, rising through the floor, through the foundations of the building, up out of the deep rock of the planet itself. And they do not stop for you. They do not stop for anything. They pass straight through your body, straight through the bed, straight through the whole of the earth, as if all of it, you, the bed, the mountains, the oceans, the entire 6,000-kilometre thickness of the world, were nothing more solid than an open window. These particles have a name. They are called geoneutrinos. And they are, in a sense, the smoke of a hidden fire. They are the faint exhaust of a furnace buried so deep beneath your feet that no human being has ever seen it, or touched it, or ever will. And yet, by learning to catch these little ghosts, a mere dozen or two of them a year, in enormous tanks of liquid built in caverns beneath mountains, physicists have done something that would have sounded like sorcery to anyone who lived more than a lifetime ago. They have learned to weigh that furnace, to measure the fuel inside a planet without ever going down to look at it, to read the heart of the earth from the outside, the way a doctor listens to a heartbeat through a wall of skin and bone. That is where we are going tonight. Down to the furnace, and then further still, down to the question of how anyone could possibly know it is there. But let us not rush the descent. Let us start with a simple, almost childlike question, the kind of question you might have asked as a small child staring at a campfire, half asleep, the flames turning to shapes behind your eyelids. Why is the inside of the earth still hot? Think about that for a moment. Gently. The earth is old. Not old the way a grandmother is old, or old the way an ancient tree is old, or even old the way a mountain is old. The earth is 4.5 billion years old. That is a number so large it slides right off the mind, like water off a stone. And in all that unimaginable stretch of time, the planet has been sitting out here in space, in the deep cold of the void, where the temperature is hundreds of degrees below freezing, radiating its warmth away into the endless dark, night after night after night, for billions of years without pause. A cup of tea left on the counter goes cold in an hour. A stone pulled from a bonfire is cool by morning. A house with the heating switched off surrenders its warmth to the winter in a single night. Everything warm, left alone long enough, grows cold. That is one of the deepest and most reliable truths we know about the world. Heat flows from warm things to cold things, always patiently, until they match. The tea and the room become the same temperature. The stone and the night become the same temperature. Everything, given time, comes to rest. So the Earth, sitting for 4.5 billion years in the cold of space, ought to have gone cold long ago, cold all the way through. A dead stone, hard and still and lifeless. Its heat surrendered to the void an eternity ago. And yet it hasn't. Dig down. Not that we can dig very far, as you'll see, but dig down even the little way that miners and drillers have managed, and the world grows warmer with every step. Go down into the deepest gold mines of South Africa, 2, 3, 4 kilometers beneath the surface, and the rock walls are hot to the touch, so hot that the miners work in air that must be cooled and pumped down to them. Or they would not survive. Go deeper, in your imagination, past anywhere a person has ever stood, and it grows hotter still. Down at the very center of the Earth, some 5,000 kilometers beneath your bed, the temperature is thought to be around 5,000 to 6,000 degrees, as hot as the glowing surface of the sun itself. A little sun, hidden inside the Earth, that has refused to go out for 4.5 billion years. How? What keeps it burning? What refills the warmth that should have leaked away into the cold of space an eternity ago? That is the mystery. And the answer, the real, astonishing, true answer, is not the one most people carry in their heads. If you ask most people why the inside of the Earth is hot, they will tell you something about the molten core. The core is made of liquid iron, they'll say, and it's leftover heat from when the planet formed, and it's slowly cooling down, and one day it will go cold. And there is truth in that. There is a molten layer down there, an ocean of liquid iron. And some of the heat is indeed left over from the planet's fiery birth. But that is only half of the story. Quite literally, as it turns out, only about half. Because the buried furnace beneath your feet has not one source of fuel. It has two. And they could hardly be more different from one another. The first source is old, very old. It is the heat of creation itself, the warmth of the day the Earth was born, sealed inside the rock, like the last embers of a fire banked down beneath ash. When the planet formed 4.5 billion years ago, it did not come into being gently. It was built out of violence, out of countless collisions, out of rock slamming into rock, out of the entire young Earth being hammered together, piece by piece, from a storm of debris circling the newborn sun. Every one of those impacts turned motion into heat, the way a nail turns hot when you strike it again and again with a hammer, the way your hands grow warm when you rub them together on a cold morning. Multiply that by 100 million years of relentless bombardment, and the whole young planet glowed. It was, for a time, an ocean of molten rock from top to bottom, a world of fire. And then, as the iron in that molten world sank down toward the center, pulled by gravity to form the core, that sinking released even more heat. A vast surrender of energy as the heaviest material fell inward toward the middle of the planet. So the Earth was born burning, and a great deal of that birth heat is still down there, still leaking slowly outward, still keeping the interior warm. It is the oldest fire there is. Nothing feeds it. It only fades, but it fades so slowly, through so much thick insulating rock, that 4.5 billion years later, it has still not gone cold. That is the first half of the furnace, the leftover warmth of the beginning. But the second source is where the story turns strange and beautiful. Because the second source of the Earth's heat is not left over at all. It is being made right now. this very second. As you lie here breathing, deep inside the rock beneath you, new heat is being created, not remembered from the birth of the world, but freshly born, this instant, and the next, and the next. How? By the quietest process in all of nature, by atoms falling apart, scattered all through the rock of the earth, through the mantle, through the crust, through the very ground your house stands on, are certain special atoms. They are radioactive. And radioactive is a frightening word, a word that brings to mind sirens and warnings and disaster. So let me take the fear out of it, gently, right here in the dark. A radioactive atom is simply an atom that is unstable. It cannot hold itself together forever. And so at some unpredictable moment, entirely on its own, with no cause and no trigger, it comes apart. It breaks. It transforms itself into a different, more stable kind of atom, and in doing so, it lets go of a tiny puff of energy, a tiny flash of warmth. One atom coming apart is nothing at all, less than nothing. You would never feel it, never notice it, could never in 1,000 lifetimes detect a single one. But there are not one, or 1,000, or 1,000,000 of these atoms in the earth. There are numbers of them beyond any counting, uncountable trillions upon trillions. Spread through every cubic meter of rock in a planet 8,000 miles across, and each one, when its moment comes, lets go of its little breath of heat. And all those tiny breaths together, across the whole enormous body of the earth, add up to a warmth that never stops, a fire with no flame, a furnace that burns by the slow and silent crumbling of atoms. That is the revelation at the heart of tonight's story, and it is worth holding on to as you drift. The earth is not simply a cooling ember, a warm stone slowly surrendering the heat of its birth. It is that, but it is also something more alive. It is a planet that is in part still heating itself, still generating fresh warmth deep in its bones, moment by moment, atom by atom. As it has since before there was any life on its surface to feel it. Half old, half new, half the fading warmth of creation, half a fire that is lit again and again, forever, one crumbling atom at a time. Roughly 50-50, as best we can tell, though I want to be honest with you here in the quiet, because the truth is more soothing than any false certainty. We do not know the split exactly. It might be a little more of the old, a little less of the new, or the other way round. The best measurements gather right around half and half, and that is a wonderful thing to know, but the edges of the number are soft. And there is something restful in that, isn't there, that even the people who study this most closely will tell you, about half. Roughly half. We are still listening, still measuring, still learning to weigh a fire we cannot see. Now here is a thing that surprises almost everyone, and it is the kind of quiet, humbling fact that is perfect for the slow hours of the night. For all that we call it a furnace, for all the talk of fire and molten iron and heat like the surface of the sun, the total warmth escaping from inside the earth is, in one very real sense, astonishingly faint. Add it all up, every bit of heat leaking out of the entire planet, from every volcano and every hot spring, and every square inch of ordinary ground, all of it together, everywhere on Earth, at once. The number comes to something like 44 to 47 trillion watts. 44 trillion. It sounds colossal, and in total it truly is. It is more power than all of human civilization uses, many times over. It is a genuinely vast river of energy pouring up out of the ground. And yet, spread that vast river out over the whole surface of the planet, over all the continents and all the ocean floors, every field and forest and city and sea, and at any one spot under your own feet. The heat coming up out of the ground is almost nothing. It amounts to less than 1/10 of a watt for every square meter of ground. Not enough to warm your palm if you laid it flat against the earth on a cold day. Not enough to melt a snowflake. A candle gives off more heat than a square meter of the planet's surface. The furnace is real, and it is enormous in total. But stretched across a whole world, it becomes the faintest imaginable whisper of warmth, a heat you could never feel, seeping up from below so gently that it takes the most delicate instruments in the world even to notice it is there. Compare it to the sun. On an average day, averaged over the whole globe, day and night together, sunlight pours down about 340 watts onto every square meter of the earth. 340 from the sun against less than 1/10 of a watt from below. The sun delivers roughly 3,000 to 4,000 times more heat to the surface than the whole buried furnace of the planet can push up from beneath. When you feel the warmth of a summer afternoon on your skin, you are feeling the sun, entirely the sun, and not in any way the fire at the center of the earth. And that is worth pausing on, softly, because it clears away a small confusion that some people carry. The sun warms the surface. The sun does not warm the inside. Sunlight sinks only a little way into the ground, a few meters, no more, before it is soaked up and given back to the sky each night. It never reaches the deep. The furnace inside the earth owes nothing to the sun. It is entirely the planet's own, half the memory of its violent birth, half the endless quiet crumbling of atoms in the dark. The sun lights the day, but the fire in the deep is lit from within and always has been. So we have a furnace that is, per footstep, fainter than a candle, and yet in total, across the whole planet, a river of 44 trillion watts, a whisper underfoot that becomes a roar when you add up the whole world. And half of that whisper is being made, right now, by atoms falling apart in the rock. Which atoms? This is where the story gains its precise and lovely detail, the sort of small, true facts you can turn over slowly in your mind as your breathing deepens. It is not just any atoms that do this heating. It comes down almost entirely to just 4 kinds, 4 particular ingredients, scattered through the rock in the tiniest traces, a few parts in a billion, here and there, no more, and yet between them they light half the fire of an entire planet. 4 names. Say them slowly to yourself as I do, and let them settle. They are ancient words for ancient things. The first is uranium. Not one kind of uranium, but two slightly different versions of the same element. There is uranium-238, the common, patient, long-lived kind, the workhorse of the deep fire, and there is uranium-235, its rarer, faster cousin, the one that burns through itself more quickly. 2 uraniums, then, one slow and one quick, both crumbling away in the rock and giving up their warmth. The third is thorium. Thorium-232, to give it its full and proper name, a metal even more patient than uranium, even slower to come apart, a substance that keeps its warmth in reserve across spans of time that make the age of the earth itself look brief. We will come to just how patient thorium is, and it is one of the most beautiful facts in all of this. But for now, simply hold the name. Thorium, the slow log at the back of the fire, glowing on and on and on. And the fourth is potassium. Potassium-40, one particular rare version of an element that is otherwise entirely ordinary. The same potassium that is in a banana, in your own blood, in the salt substitute on a kitchen shelf. Most potassium is perfectly stable and harmless. But a tiny fraction of it, this one special form, potassium-40, is unstable and slowly falls apart and adds its own small breath of warmth to the furnace far below. Uranium-238, Uranium-235, Thorium-232, Potassium-40. 4 names, 4 kinds of atom, threaded through the rock of the world in traces so faint you could hold a fistful of that rock and never dream of the fire sleeping inside it. And between just these 4, half the heat of the entire planet is kindled and rekindled endlessly in the dark. There is something almost tender about it when you sit with it in the quiet. The earth is not warmed from within by roaring flame or churning lava. Not really, not in the way the childhood imagination pictures it. It is warmed by 4 faint ingredients, present in the merest whisper of a quantity, doing the smallest possible thing, a single atom, now and then coming quietly apart, and doing it so many countless times over, in so much rock, across so much time, that the whole vast interior of a planet is kept warm against the cold of space by nothing grander than that. The patient crumbling of a few rare atoms, unfelt, unheard, unseen, holding back the cold of 4.5 billion years. And it raises the question we will spend the rest of our slow journey answering, the question that turns this from a pretty story into something almost miraculous. If these 4 ingredients are buried so deep, in such tiny amounts, mixed through thousands of kilometers of rock we can never reach, how could anyone possibly know they are there at all? How could anyone measure a fire nobody has ever seen, fueled by atoms nobody has ever held, burning in a place no human hand will ever touch? How do we know it is uranium and thorium and potassium down there and not something else, or nothing at all? How do we know the split is roughly half and half? How do we weigh a furnace at the center of a world? That is the ghost we began with, the million little particles passing through your body every second, up out of the deep. They are the answer. They are how we know, and we will follow them. Gently, all the way down and all the way back up, before this night is through. But before we learn to catch the ghosts, we have to understand the clock they keep. Because each of those 4 ingredients, the 2 uraniums, the thorium, the potassium, comes apart at its own particular pace, its own rhythm, its own slow and steady heartbeat, measured not in seconds or years, but in hundreds of millions and billions of years. And those rhythms are among the most extraordinary numbers in all of science. Numbers so vast and so patient that they were made, it almost seems, to be spoken aloud in the dark, at the edge of sleep, to a mind letting go of the day. So let your breathing slow a little more. Let the 4 names drift in the warm dark below you: uranium, uranium, thorium, potassium, 4 faint fires in the deep rock, each keeping its own ancient time. And as you sink toward rest, hold on to the gentle strangeness of where we have arrived. Beneath you, right now, a furnace older than the oceans, older than the continents, older than life itself, is burning without a flame. Half of it is the warmth of a world being born in fire and violence, so long ago that the number means nothing to the human heart. And half of it is being made this very instant, atom by atom, breath by breath, in a silence so complete that it took some of the cleverest people who ever lived to hear it at all. And they heard it. That is the wonder we are moving toward. They found a way to listen to the heart of the earth, not with a drill, not with a shovel, but by catching the ghosts that rise up through the ground, the faint particles slipping through your body even now, 1,000,000 a second, carrying with them the secret of how much fire is buried below, and what it is made of, and how long it has yet to burn. We have only just begun the descent. There is so much more warmth to sink into. The clock of the four fires, and how one of them keeps time longer than the universe itself. The great mistake of a brilliant man who once declared the earth far too young before this hidden fire proved him wrong. The tanks of liquid buried beneath the mountains where the ghosts are caught, one by one, a mere handful a year. And, at the very end of the long night, a smaller world, a colder world, a planet that once had a fire just like this one, and lost it. Its name is Mars, and its silence has something to teach us about why our own world still breathes and stirs and lives. But all of that is for the deeper dark ahead. For now, there is only this: a furnace beneath you, faint as a candle underfoot, yet vast as 44 trillion candles all at once, half as old as time and half as young as this moment, kept alive by 4 quiet ingredients crumbling in the rock. It has burned since before there was anyone to feel it, and it is burning now, patiently, warmly, holding back the cold as you let go of the day and begin, at last, to drift downward into rest. Let us stay here a while longer at the surface before we go down. Because the strangest thing about this fire is how gentle it feels from where you are lying. Put your hand flat against the floor. Feel nothing. No warmth rising. No trembling. And yet the heat is there, leaking upward through every square inch of ground on the planet, all the time, without pause. Measure it, and you find only about 87 thousandths of a watt for every square meter of the Earth's surface. Less than a tenth of a single watt. Not enough to warm a fingertip. Not enough to notice in 10,000 lifetimes of noticing. That is the paradox we will hold in our hands tonight, almost nothing underfoot. And yet, add it up. Take that faint whisper of heat and spread it across the entire skin of the world, across every ocean floor and mountain range and frozen plain and buried valley, and it swells into something almost past imagining. 44 trillion watts, by some careful measurements, closer to 47. A furnace so large the number stops meaning anything, and so quiet you could sleep on top of it your whole life and never once feel it stir. Compare it to the other fire, the one you know. The sun pours down more than 300 watts onto every square meter of the Earth, averaged over the whole turning globe. Set that beside the 87 thousandths coming up from below. And the buried furnace is something like 3,000 or 4,000 times fainter beneath your feet than the daylight is upon your face. Which is why, for most of human history, no one thought to look down for a fire at all. The great warmth of our lives has always come from above. The sun rises, the ground warms, and it feels, doesn't it? As though the heat of the world is simply borrowed sunlight sinking in. But it isn't. Here is the quiet correction, and then we will let it go. The sun does not heat the inside of the earth. Its warmth reaches only a few meters into the soil before the ground gives it all back to the sky again by morning. Everything deeper than that shallow skin, everything that matters in this long story, is heated from within. The furnace is entirely the Earth's own. It owes the sun nothing. So where does it come from, this fire that answers to no star? This is the heart of the mystery, and the answer, when it finally arrived, split neatly into 2 halves, 2 fires, really, braided so closely together that for a long time no one guessed there were 2 at all. The first fire is old. It is the oldest thing there is, older than the oceans, older than the first stone. It is the heat of the planet's own birth. When the Earth was gathering itself out of dust and rock and falling debris, Every collision, every fragment slamming into the growing world gave up its motion as warmth. And when the heavy iron sank inward to form the core, all that falling released a flood of heat that soaked the entire young planet through. That warmth has been leaking away ever since, slowly, over 4.5 billion years, a memory of creation still glowing faintly in the dark. Roughly half of everything escaping through the ground beneath you tonight is that ancient heat, the earth remembering the day it was made. And the other half is being made right now. This is the part that took the longest to believe, because it asks you to imagine fire without flame. Deep in the rock, mostly through the mantle and the crust, closer to your bed than to the planet's center, there are certain atoms that are not stable. They cannot hold themselves together forever. One by one, on their own private schedules, they come quietly apart, and each time one does, it releases a tiny breath of energy. A single one is nothing, but there are so many of them, uncountably many, crumbling steadily through the whole vast body of the earth, that all those tiny breaths together add up to something on the order of 20 trillion watts of fresh heat, generated this very second, and the next, and the next. Roughly half of the furnace, then, is not left over at all. It is alive. It is being lit continuously as you fall asleep by the slow undoing of the rock itself, and it comes down to just 4 ingredients. 4 out of everything on the periodic table, out of all the elements that make up the earth. Nearly the entire ongoing fire is fed by only these. There is uranium, 2 kinds of it actually, a heavier and more patient one the scientists call uranium-238, and a rarer, faster-burning cousin, uranium-235. There is thorium, thorium-232, the slowest and most patient of them all. And there is a form of ordinary potassium, potassium-40. A trace of the same element that runs through your own blood and the soil of every garden, quietly radioactive, quietly warming the deep. Uranium-238, uranium-235, thorium-232, potassium-40. 4 names. That is the whole recipe of the living half of the fire. Say them slowly and let them settle, because we will return to each of them in the hours ahead, and each has a story stranger than the last. 2 fires, then, in near-perfect balance. About half born the day the world began, about half made new in this passing moment. Not exactly half and half. The honest truth is that no one can pin the split to the last decimal, and the scientists are careful to say about, but close enough that the symmetry of it feels almost designed. Ancient heat and living heat, leaking upward together through the ground, meeting under your feet as a single faint warmth you will never feel. And the ghosts. Come back to the ghosts one more time before we begin the descent in earnest. Every one of those countless little undoings deep in the rock, every uranium atom, every thorium atom coming apart sends out a particle so slight, so nearly weightless that the entire mass of the planet cannot stop it. They rise through the mantle as if it were open air, through the crust as though it were nothing. Up through the floor, up through the bed, up through you, a trillion of them crossing every second, silent, harmless, utterly unfelt. Each one a tiny messenger, carrying word of the fire that made it, streaming out into the night sky and away. For most of history, no one knew they were there. So let us begin there, with time, with the clocks inside the furnace, because the most remarkable thing about those 4 fuels is not simply that they burn, but how long they have been burning, and how long they will go on. Uranium-238 is the slowest of them, patient beyond any ordinary measure of patience. Its half-life, the time it takes for exactly half of any given sample to decay, to come apart one atom at a time and release its small portion of heat, is approximately 4.5 billion years. 4.47 billion years, to be more precise about it. And if that number sounds familiar, it should. The Earth itself is roughly 4.5 billion years old, which means that when this planet first formed, coalescing from dust and rock and collision in the early solar system, it came equipped with a certain quantity of uranium-238, and today, sitting here in the dark, about half of that original supply is still here, still intact, still decaying, atom by patient atom, releasing warmth into the rock around it. The other half has already come apart, slowly, over all the eons between the birth of the world and this night. But the remainder presses on, unhurried, ticking at the same rate it always has. Think of it this way. Imagine you lit a candle at the moment the Earth formed. 4.5 billion years later, now that candle is half burned down, not extinguished, not guttering, half burned, and it has roughly another 4.5 billion years before it reaches the halfway point again. Uranium-238 is that candle. It has barely gotten started by any reasonable reckoning of time. This is not a metaphor for drama. This is a metaphor for scale, for the almost incomprehensible patience of geological processes. The furnace was not made in haste. It will not go out in haste either. It runs on clocks so long that the human mind, evolved to track seasons and lifetimes, has to be coaxed into even approximating them. Now move to thorium-232. The second of the four fuels, and in some ways the most extraordinary of them in its relationship with time. Thorium-232 has a half-life of approximately 14 billion years. 14 billion. Stop for a moment with that number. The current age of the universe, from the first fraction of a second after the Big Bang to this present night, the whole of cosmic history as we understand it, is roughly 13.8 billion years. Thorium-232's half-life is longer than that, longer than the age of everything. What that means, practically, is that the thorium sitting in the rock beneath you has barely decayed at all since the Earth formed. Not even half of it has come apart yet. The amount of thorium present in the planet's mantle and crust today is very nearly the same amount that was there at the beginning. It is the slowest log on the fire, the most patient fuel. If uranium-238 is a candle half-burned in 4.5 billion years, thorium-232 is a log that has been smouldering since before stars existed and has barely scorched its outer surface. There is something almost calming about this, if you let yourself settle into it. The slowness is not a failure of the furnace, it is the furnace's great gift to us. Because it burns so slowly, because these half-lives are measured in billions of years rather than years or centuries, the heat it produces is essentially constant on any timescale a living creature could perceive. You will not notice a change in the warmth rising from below over a human lifetime. Your children will not notice it. A civilization lasting 10,000 years would not measure any meaningful difference in the rate of heat flowing up from depth. From the perspective of anything alive, the furnace is steady, the same today as it was when the first fish crossed from sea to land. The same as it was when the dinosaurs walked across what would someday become the ground beneath your house. A deep, permanent, geological heartbeat. Potassium-40 is different, not slower, but stranger. Its half-life is approximately 1.25 billion years, shorter than either uranium or thorium. which makes it the most energetic of the three in terms of how quickly its contribution diminishes over geological time. But potassium-40 has a peculiarity the others lack, a fork in the road of its decay that makes it remarkable in a different way entirely. When uranium-238 decays, it follows a long chain of intermediate steps, eventually arriving at lead. When thorium-232 decays, it follows its own chain and also ends at lead. These are well-worn paths, predictable, one-directional. But potassium-40 decays two ways simultaneously. About 89% of the time, a potassium-40 nucleus becomes calcium-40. That is the more common branch, and it is how potassium quietly builds calcium in the rock, a fact with its own geological interest, but not the peculiarity I mean. The remaining roughly 11% of the time, potassium-40 does something else. It captures one of its own inner electrons, or it decays a different way, and it becomes argon-40. Argon, a noble gas, and that matters enormously, because argon-40 is not a solid. It is a gas, and once formed inside a crystal lattice it can escape. Over billions of years, potassium-40 decaying throughout the Earth's crust and mantle has been producing argon-40 and releasing it, gradually, constantly, seeping upward through the rock, reaching the surface, entering the atmosphere. Today, argon makes up about 1% of the air you are breathing. That 1% is largely the daughter of radioactive potassium-40. Every breath you take contains the exhalations of the deep Earth's furnace, not as heat you can feel, but as a gas you cannot see, a ghost of decay made physical, mixed invisibly into every lungful of air every creature on this planet has ever drawn. The air itself is partly the furnace's signature. The thought is worth sitting with quietly. Then there is uranium-235, the fourth of the four named fuels, and in some ways the most instructive for understanding how the furnace has changed over time, because uranium-235 burns fast. Its half-life is approximately 704 million years, short on a geological scale, only about 1/6 of the Earth's age, and because it decays quickly, much more of it existed in the early solar system than exists now. When Earth formed, uranium-235 was far more abundant relative to uranium-238 than it is today. It was a more vigorous fuel then, putting out heat at a higher rate. Today, most of the uranium-235 that once existed in the planet has already spent itself, transformed through its decay chain into lead-207, and what remains is only a fraction of the original supply. Uranium-235 is the fast burner, and the fast burner has already done most of its burning. This matters because it means the Earth's radiogenic furnace, the living, decay-powered half of the heat budget, was not always running at the rate it runs tonight. Go back 4 billion years to the early Earth, and the picture is different. The uranium-235 was more abundant. And there was something else, a fifth fire that no longer burns at all, that burned so furiously in the infancy of the solar system that it shaped the very bodies the planets are made of. Its name is aluminum-26, an isotope of aluminum, but nothing like the ordinary aluminum-27 that makes up almost all the aluminum you encounter in daily life. Aluminum-26 is unstable, radioactively unstable, with a half-life of only about 717,000 years. Not billions of years, not hundreds of millions. 717,000. In geological terms, that is less than a heartbeat. It burned almost entirely in the first 1,000,000 or 2,000,000 years after the solar system formed, releasing heat at a prodigious rate as it did so. And it left. It decayed into magnesium-26, and went silent, so completely that none of it remains anywhere in the solar system today. Every atom of aluminum-26 that ever existed in the early solar nebula has long since transformed into something else. But while it burned, it mattered enormously. The planetesimals, the small rocky bodies, the building blocks from which the planets grew, contained aluminum-26 from their formation, and the heat it produced was enough to melt them internally. To differentiate them, to separate the iron from the rock, the dense from the light, rearranging their interiors into layered structures. The heat of aluminum-26 was the furnace that did the first great sorting of material in the early solar system, the fire that ran hot and brief and left its mark on everything before vanishing utterly. It is, in a sense, the fire that already went out, the memory of a fuel so short-lived that even the oldest rocks on Earth cannot remember it, because by the time the Earth was fully formed, it was already gone. Between aluminum-26's early blaze and the ongoing contributions of uranium-235 in the planet's youth, the radiogenic heat of the early Earth was substantially higher than it is now. Current estimates suggest that roughly 4 billion years ago, the rate of heat production from radioactive decay was somewhere between 2 and 5 times greater than it is today. The furnace ran hotter when the Earth was young. Not because the primordial heat had not yet leaked away, though that is also true, but because the living, decay-powered half of the budget was itself larger then, fed by fuels that have since diminished. The planet has been slowly banking down. The furnace has been cooling almost imperceptibly since the beginning. But it has 4.5 billion years of cooling already behind it, and is still running at 44 to 47 trillion watts tonight. It has some time left yet. Now, there is a misconception that needs correcting, and it is one so deeply embedded in the popular image of the Earth's interior that most people carry it without ever having examined it. When people imagine the heat of the deep Earth, they tend to imagine it rising from the center, from the core, the iron heart of the planet, glowing in the dark. That is the mental picture most of us have assembled from films and school lessons, and the instinctive sense that heat comes from deep down, and deeper is hotter, so the deepest part must be the source. But the radioactive fuel, uranium, thorium, potassium-40, is not in the core. It is not at the center. It is up here, near you. This requires some explanation, because it is counterintuitive, and the explanation is elegant in the way that chemistry can sometimes be. Uranium, thorium, and potassium-40 are what geochemists call lithophile elements. That word means rock-loving, from the Greek lithos for stone. These elements have a strong chemical affinity for silicate minerals, for the compounds of silicon and oxygen that make up ordinary rock, and they avoid metallite phases, which is to say they avoid iron. During the very early history of the Earth, when the planet was largely molten and iron was separating from silicate rock and sinking toward the center to form the core, that great event that geologists call the iron catastrophe. When the heaviest material in a liquid planet migrates inward under gravity, the lithophile elements were left behind. They had no chemical interest in going with the iron. They stayed in the silicate material, in what would become the mantle and the crust. The iron core formed around them, beneath them, and they stayed where they were, concentrating in the rocky part of the planet, while the iron departed for the center. The result is that the core today contains essentially no uranium, no thorium, no potassium-40 in any significant quantity. The radiogenic heat source is not at the bottom of the system. It is distributed through the mantle and concentrated especially in the continental crust, the rock you are sitting on, the rock that forms the continents, the rock that is geologically old and chemically enriched and holds the fuel closer to the surface than to the planet's heart. Continental crust, the thick, ancient, granitic rock that underlies the continents, can contain uranium and thorium at concentrations of several parts per million. Several parts per million might sound vanishingly small, and by everyday standards it is. But the crust is vast, and the heat from even trace concentrations of these isotopes adds up over the immensity of geological volume and geological time. The mantle below holds uranium and thorium at far lower concentrations, parts per billion, roughly 1,000 times more dilute than the crust above, but the mantle is enormous, far larger in total volume than the crust. And so its contribution to the total radiogenic budget is still significant. The core contributes nearly nothing to the radiogenic heat. There is some debate, carefully maintained in the scientific literature, about whether a small amount of potassium-40 might have partitioned into the core under the extreme pressures of core formation. Potassium is a somewhat different chemical case than uranium and thorium, and under high-pressure conditions, some silicate-incompatible behavior might occur. The debate is real, and the question has not been entirely settled. But even optimistic estimates of potassium in the core represent a small fraction of the total budget. For all practical purposes, the radioactive fuel is in the rock, not in the iron. The reactor is in the walls of the house, not in the basement. This is one of those facts that, once you hold it clearly, changes the picture you carry of the deep earth. The furnace you feel rising through the planet is not rising entirely from the center. A significant portion of it is rising from just beneath your feet, from the crust itself, from the rock a few tens of kilometers below any continental surface, from the granite and gneiss and schist that is the ancient skeleton of the continents. The uranium in the ground is not a figure of speech. It is the fuel of the planet, and it is closer to you than to the core. The mantle between the crust and the core carries the rest of the radiogenic heat, distributed through its immense volume at concentrations that are individually tiny but collectively meaningful. And all of it, every bit of uranium-238 and thorium-232 and potassium-40 and the fading contribution of uranium-235 has been sitting in that rock, locked in mineral crystals, slowly coming apart since the planet formed, slowly releasing heat, slowly warming the rock around it. The rock conducts that warmth upward, imperfectly, at the pace of geology, which is to say, at a pace that makes even the slowest of human processes feel frantic. Because here is the other number that deserves its own moment of quiet attention. The Earth's mantle, the vast body of rock between crust and core, the slow plastic stone that makes up most of the planet's volume, is cooling at a rate of approximately 100 degrees Celsius per billion years. Some estimates put it as low as 50 degrees per billion years, some a bit higher. But the order of magnitude is clear. 100 degrees per billion years. 100 degrees is not nothing. Applied all at once, that is the difference between ice water and boiling water. It is a significant temperature change in any context a living creature might care about. But spread across 1 billion years, 1,000 million years, it is almost nothing at all. Divided across 1 billion years, it is 1/10,000,000th of a degree per year. A quantity so small that no instrument built by human hands could detect it in a human lifetime. Over your entire life, the mantle beneath you will cool by an amount smaller than the uncertainty in measuring it. This is the pace of the furnace's decline. Not dramatic, not urgent, not the rushing out of a fire starved of oxygen, the guttering of a candle in wind. Just this, a slow, majestic, geological banking down, as unhurried as the elements themselves. The same way thorium's clock ticks so slowly that the universe has not yet lived long enough for it to reach its first half-life. The furnace cools on timescales that dwarf any human category of slowness. There is comfort in this if you are the kind of person who finds comfort in vastness. Nothing here is sudden. The warmth that has been rising through the ground since the beginning of the earth has not changed appreciably since the first bacteria moved through the early ocean. It will not change appreciably by the time whoever inherits this planet finally learns to look inward and understand what they stand on. The fire is patient, it keeps its own schedule, and that schedule is written in the half-lives of atoms, in the mathematical certainty of quantum decay, in numbers so large that language was never quite designed to hold them. And yet those numbers are known. That is the remarkable thing. That is what makes this story something more than ancient mystery wrapped in geological scale. We know the half-life of uranium-238 to high precision, 4.47 billion years, not because we have waited 4.5 billion years to watch it, which would be somewhat impractical, but because we have measured the rate of decay directly in laboratory samples, counted the events per second per gram, and extrapolated. The mathematics of radioactive decay is among the most precisely tested quantitative relationships in all of science. Given a sample of uranium-238, you can calculate exactly how many atoms will decay in the next year, the next century, the next billion years, with a confidence that borders on the absolute. The clocks are not estimates, they are measurements. Thorium-232, 14.5 billion years, give or take a small fraction. Potassium-40, 1.25 billion years. Uranium-235, 704 million years. These are not approximations in the sense of guesses. They are measurements, done with increasing precision over more than a century of nuclear physics, and they are the foundation on which everything else about the furnace is calculated. Because once you know the half-lives, and once you know how much of each isotope the Earth contains, which is itself a separate and fascinating question that we will come to, you can calculate exactly how much heat each isotope is producing right now, tonight, in the rock below. The rate of decay is the rate of heat production. One follows from the other with the force of mathematics. The question of how much of each isotope the Earth contains is where things get complicated and where a particular kind of ingenuity becomes necessary. Because the Earth is large and mostly inaccessible, and we have not yet managed to drill to any depth that would give us a representative sample of the mantle, let alone the deep mantle, let alone the boundary with the core. The deepest hole humanity has ever bored into the planet, the Kola Superdeep Borehole in Russia, a project of almost surreal ambition that ran from 1970 until funding ended in the 1990s, reached a depth of approximately 12 kilometers and 26 meters, 12.26 kilometers. That is not a number to dismiss. It represents decades of engineering at the absolute edge of what heat and pressure and economics allow. But 12 kilometers, set against the 6,371 kilometers from surface to the Earth's center, is less than 0.2% of the distance, not even through the crust in most places. The deepest borehole ever drilled did not reach the mantle. We have never pulled up a sample of mantle rock from in place, from its natural position at depth. We know mantle rock exists. It reaches the surface through volcanoes and through certain geological upwellings, and we can study those samples, which is enormously informative. But a direct chemical inventory of the whole Earth's interior, carried out by drilling and sampling, is simply beyond us. The planet is too large, the pressures too immense, the temperatures too high. At 12 kilometers depth, the temperature in the Kola borehole was already around 180 degrees Celsius, far hotter than the geologists expected, a reminder that the furnace, faint as it is at the surface, grows significantly more emphatic as you descend. So we read the interior by other means. We read it the way you might read the interior of a sealed room from the sounds it makes, by listening. Seismic waves from earthquakes travel through the Earth's interior, bending and reflecting and changing speed as they cross boundaries between different kinds of rock and fluid. By studying the patterns of those waves at monitoring stations distributed around the globe, we have built a picture of the Earth's internal structure in extraordinary detail. We know where the crust ends and the mantle begins. We know where the mantle ends and the outer core begins. We know the outer core is liquid, not because anyone has been there, but because certain kinds of seismic waves cannot pass through liquid, and the shadow of that absence. The zone where those waves do not arrive first gave Benno Gutenberg, working in 1913, the shape of a liquid region at depth. And we know there is a solid inner core within the liquid outer core because Inge Lehmann, a Danish seismologist working in 1936, noticed that certain reflected seismic waves arriving in the shadow zone could only be explained by a solid object nested inside the liquid one. We have mapped the deep earth with sound, with mathematics, with the patient analysis of earthquake waves. And we have built models, the bulk silicate Earth model, which attempts to reconstruct what the chemical composition of the entire silicate portion of the planet must be, based on our knowledge of meteorites, of the solar system's original composition, of what we find at the surface and near it. These models give us estimates of how much uranium and thorium and potassium the planet contains, and from those estimates we can calculate the expected radiogenic heat. But models are models. They are not direct measurement. They carry uncertainties. They can be wrong in ways their builders do not immediately recognize. Because a model is a simplified picture of something real and complex, and the simplifications are always imperfect. The question of how much heat the Earth's radioactive decay is actually producing, tonight, in the rock, in real atoms coming apart in real crystal lattices, could not be answered from models alone with the precision scientists wanted. The planet was keeping that number to itself, buried under kilometers of rock and pressure, until the particles came to the rescue, until the ghosts arrived. Go back for a moment to what happens when a uranium-238 atom decays. It does not simply convert into another element and release heat. It releases several things simultaneously. Energy. Yes, kinetic energy in the recoiling daughter nucleus and in the emitted alpha particle, energy that becomes thermal energy as those particles bump against neighboring atoms and slow down, which is the heat we have been discussing. But it also, in some steps of the decay chain, releases an antineutrino, a particle of almost no mass, no electric charge, travelling at very nearly the speed of light, interacting with matter so weakly that it passes through essentially everything. The antineutrinos from uranium and thorium decay in the deep earth rise upward through the planet the same way the heat cannot, straight through, unimpeded, in all directions, out into the night. They are called geoneutrinos when they come from the Earth itself, to distinguish them from the far more numerous neutrinos arriving from the Sun and from cosmic ray interactions in the atmosphere. And they carry information. Because the energy of a geoneutrino is directly related to the decay that produced it, uranium decays produce antineutrinos in a specific energy range. Thorium decays produce them in a somewhat different range, and because the number of geoneutrinos streaming out of the Earth per second is directly proportional to the number of uranium and thorium atoms currently decaying, which is directly proportional to how much of those elements the planet contains. Count the geoneutrinos, measure their energies, and you have, in principle, weighed the furnace. Not estimated it from models. Weighed it, with particles, directly, roughly 1 million of these geoneutrinos pass through every square centimetre of your body every second. Through the surface you are lying on, through the air above you, through the ceiling, through the roof, through whatever is above that, and on out into space. 1 million per square centimetre per second, ceaseless, harmless, utterly without consequence for anything biological. They are there right now, streaming through this room, through you, through the bed, through the Earth's crust below, and away. Every single one of them carries a tiny record of a radioactive decay deep in the rock, a particle-sized message from the furnace. For most of history, no one could read those messages, because detecting a particle that passes through a planet without noticing it requires something extraordinary, a detector large enough and sensitive enough to catch the rare, vanishingly rare event when one of those geoneutrinos actually does interact with something. The interaction rate is so low that you could sit a single proton in the path of a geoneutrino beam and wait, on average, longer than the age of the universe for one collision to occur. The particles are not just abundant, they are astonishingly reluctant to stop. The solution is not to make the target more receptive, the solution is to make the target immense. Fill a tank, not a small tank. A tank holding 1,000 tons of liquid scintillator, a special organic fluid that emits a tiny flash of light when a charged particle moves through it. Surround that tank with thousands of light-sensitive detectors, photo-multiplier tubes that can register single photons. Bury the entire apparatus under a mountain so that the rock above filters out the noise of cosmic rays that would otherwise swamp the faint geoneutrino signal. Then wait. And count. And when a geoneutrino finally collides with a proton in the liquid scintillator, it produces a positron and a neutron, a process called inverse beta decay. And that positron immediately annihilates with a nearby electron, producing 2 gamma rays, and then a fraction of a second later the neutron is captured and produces another gamma ray, a distinctive delayed coincidence double flash that is the unmistakable fingerprint of an antineutrino interaction. One flash, then another, a tiny interval later. That is the signal. And the counts are small. Astonishingly small. A year of watching might yield a handful of confirmed geoneutrino events, a dozen, perhaps a few dozen, after carefully subtracting all the other signals that might mimic the signature. Antineutrinos from nuclear reactors. Background radioactivity in the detector itself. Cosmic ray remnants that squeaked through the mountain. All of it must be accounted for, measured, subtracted, leaving behind the faint residue of the planet's own signal. It is not the work of a season, it is the work of years, of decades, of patient accumulation by large collaborations of physicists who understand that they are doing something unprecedented, reading the radioactive budget of a planet from the outside, using particles that should by all intuition be impossible to catch. The machine in Japan is called Camland. Kamioka liquid scintillator anti-neutrino detector sitting in a mine in the mountains of Gifu Prefecture, deep underground, built originally to study antineutrinos from nuclear reactors and adapted to look also at the much fainter signal from the Earth itself. In 2005, the Camland collaboration published a paper in the journal Nature. It was a short paper, as landmark papers sometimes are. Its title was Clinical, an experimental investigation of geologically produced antineutrinos with Camland. Its content was extraordinary. For the first time in history, a human-built instrument had detected geoneutrinos, had caught particles emerging from the radioactive decay of uranium and thorium in the deep earth, and counted them. The furnace had been found guilty by its own emissions. The number was small. The uncertainty was large. The signal barely rose above the noise. But it was there. The Earth was speaking in neutrinos, and for the first time someone had listened and heard something back. A few dozen events accumulated over years of watching. And humanity had its first direct experimental evidence that the planet contains radioactive fuel producing heat right now. Not merely a billion years ago, not as a historical artifact, but in the present tense, in the ongoing decay of atoms that are coming apart beneath our feet as you read these words. That was the beginning. And the story did not stop there. The story moved, as so many good scientific stories do, across an ocean and under a mountain. In central Italy, beneath the Apennines, in a laboratory carved into the Gran Sasso Massif, sits a detector called Borexino. The name is a diminutive, a small joke among physicists, though there is nothing small about it. The detector itself is a sphere of liquid scintillator, a fluid that produces tiny flashes of light when charged particles pass through it, housed inside a series of concentric shells designed to block everything the experimenters do not want to see. And they do not want to see almost everything. Cosmic rays, natural radioactivity in the surrounding rock, contamination from the stainless steel of the vessel itself. Every one of these is a potential false alarm, a ghost masquerading as a geoneutrino, and the entire experimental architecture is designed around a single goal, stripping those ghosts away until what remains, faint and real and unmistakable, is the signal from the Earth itself. Borexino sits under approximately 1,400 meters of solid rock. That overburden is not accidental. It is the shield. Cosmic rays, high-energy particles streaming in from space, are relentless at the surface, hammering through the atmosphere and into whatever they encounter, producing secondary particles that would overwhelm any detector trying to listen for something as quiet as a geoneutrino. Underground, that cosmic rain is reduced by a factor of roughly 1,000,000. The mountain does the first filtering, the concentric shielding layers inside the laboratory do the rest. And then you wait. The waiting is perhaps the hardest part to appreciate from the outside. A physics experiment at a particle accelerator can produce millions of collisions per second. The machine is always busy, always generating data. Borexino, listening for geoneutrinos, might register a genuine event, a real antineutrino from the deep Earth striking a proton in the liquid scintillator and triggering that characteristic double flash, perhaps a few dozen times per year. A few dozen. In a year of watching. To put that in proportion, on a busy highway, a few dozen cars pass in a single minute. Borexino waits a full year for the equivalent, and those few dozen must still be separated from background, from reactor antineutrinos produced by nuclear power plants scattered across Europe, from the occasional cosmic ray muon that slips through the mountain's protection. This is what it means to read the planet's interior, not with violence or drilling or any instrument that touches the Earth's substance, with patience, with subtraction, with the slow accumulation of events so rare they can be counted on a single page of a notebook. Borexino published results in 2010. It published further refined results in 2013. Its most precise analysis came in 2020, more than 15 years after Camland had opened the door. The two detectors, one in a mine in the mountains of Japan, one under the Apennines of Italy, had been listening independently on opposite sides of the planet, and they told essentially the same story. The radioactive decay of uranium and thorium in the deep Earth produces on the order of 20 terawatts of heat. 20 trillion watts, ticking away in the atoms of the mantle and the crust, generated not by any combustion or chemical reaction, but purely by the spontaneous transformation of one kind of nucleus into another, releasing energy as a matter of physical law. 20 terawatts. That is the number the neutrinos carry out of the ground and deliver to the detectors as a message. And when you hold it next to the total heat escaping the planet, roughly 44 to 47 terawatts by the best surface measurements, the implication settles in slowly. The way understanding in this subject always seems to settle in. Roughly half. Roughly half of everything the Earth loses as heat every second of every day comes not from the remnant warmth of its birth, but from atoms that are splitting apart right now. The furnace is not merely cooling, it is also being stoked. That is the number the neutrinos confirm. And the confirmation matters because for a long time, a surprisingly long time, well into the era of careful measurement, the question of how much heat was radiogenic and how much was primordial was genuinely open. Models could be built. Geochemical estimates could be assembled from surface rocks and meteorites and assumptions about how the deep Earth was put together. But a model is always a model. A count of particles that actually emerged from the planet's interior, travelled through thousands of kilometres of solid rock, and reached a tank of liquid scintillator under a mountain, that is a measurement. There is a difference between the two that matters, especially when the question at stake is the energy budget of the only planet known to harbour life. The detection method itself deserves a moment of attention, because it is one of those pieces of physics that sounds like it should be impossible, and then, once you understand it, becomes almost satisfying in its elegance. When uranium-238 decays, not in one step, but through a chain of successive transformations, each nucleus shedding particles and energy as it works its way toward a stable configuration. Certain steps in that chain involve what physicists call beta decay. A neutron in the nucleus converts to a proton, and in the process two particles are emitted, an electron and an electron antineutrino. The electron is stopped almost immediately by the surrounding matter. The antineutrino carries away a portion of the energy and continues essentially without interruption through whatever happens to be in its path. Rock, water, iron, the entire Earth. It does not care. Its interaction with ordinary matter is so feeble that most antineutrinos pass through the planet as though it were not there. But most is not all. The interaction is feeble, it is not zero. And if you have an enormous enough detector filled with a material containing a high density of protons, liquid scintillator does this, with hydrogen nuclei distributed throughout the fluid. Then occasionally, very occasionally, an antineutrino will encounter a proton at just the right moment and trigger what is called inverse beta decay. The antineutrino and the proton interact and produce two particles, a positron, the antimatter counterpart of the electron, and a neutron. The positron carries kinetic energy and almost immediately encounters an ordinary electron somewhere in the surrounding fluid. The two annihilate each other in a small flash of gamma rays, which the detector records as a prompt signal. The neutron wanders through the scintillator for a brief time, a few microseconds to a few hundred microseconds, and is then captured by a nucleus in the fluid, releasing another burst of gamma radiation. The delayed signal. A prompt flash, then a pause, then a delayed flash. That pattern, that specific time interval between two bursts of light in a specific spatial relationship, is the fingerprint. No background event mimics it precisely enough to fool the analysis at the level of confidence the experimenters require. When Borexino or Camland records that sequence, they have caught something. They have detected a single antineutrino. One, out of the trillions streaming through the detector every second, one happened to interact, and its interaction left a mark. A few dozen such marks, accumulated over months of watching, constitute the geoneutrino signal. And from those few dozen marks, physicists can infer, with appropriate uncertainties, with honest acknowledgement of background subtraction and modeling assumptions, how much uranium and thorium is dissolving into heat in the bulk of the planet below. There is an additional layer of information the detectors can extract, and it is worth naming. The antineutrinos produced by uranium-238 decay and those produced by thorium-232 decay carry different energies. Uranium antineutrinos tend to arrive with somewhat higher energies than their thorium counterparts because the uranium decay chain releases more energy per step. A sufficiently precise detector can look at the energy spectrum of the geoneutrino signal and tease apart how much of it comes from uranium and how much from thorium, reading the fuel mix, not just the total heat output. Borexino's 2020 results pushed in this direction, attempting to resolve the two contributions in the data. The separation is not yet clean, the statistics are still limited, and the two signals overlap in energy. But the principle is there, and the experimental program continues. Each passing year brings more events, better statistics, a finer resolution on the planet's hidden budget. Potassium-40 sits outside this reach. Its antineutrinos, produced when a potassium-40 nucleus decays via the beta pathway, carry energies below the threshold for inverse beta decay in these detectors. An antineutrino below that energy threshold simply cannot trigger the reaction the detector is designed to see. So potassium-40's contribution to Earth's radiogenic heat, estimated at roughly 4 terawatts by geochemical models, must be inferred from chemical arguments rather than directly counted. It is the one part of the furnace that remains beyond the neutrino method as currently practiced. Not unknown, the models are well constrained, but not yet directly weighed. That is an honest limit worth sitting with for a moment. Science, at its best, is precise about what it knows, and equally precise about where the edge of knowing falls. And now, having followed the neutrino thread as far as it currently goes, it is worth stepping back and noticing something about the isotopes at the center of this whole story: uranium-238, thorium-232, potassium-40, that goes beyond their role as heat sources. These same atoms, these same clocks ticking away in the mantle and the continental crust, are also the atoms that allowed humanity to determine how old the Earth actually is. They decay at known, fixed rates. That is their virtue as clocks. If you know how quickly a nucleus transforms, and you can measure the ratio of parent atoms to daughter atoms in a rock or a mineral, you can calculate how long that decay has been running, and therefore how long ago the mineral crystallized. This is radiometric dating. And the fact that the very same isotopes are the Earth's primary internal fuel is not a coincidence. It is a single elegant property of nuclear physics written twice into the planet's biography, once as heat and once as history. The intertwining of those two functions has a particular significance in the history of science, and it centers on a mistake made by one of the greatest physicists of the 19th century. His name was William Thomson. History knows him better as Lord Kelvin, the man whose name was given to the absolute temperature scale, the scale whose 0 point sits at -273 degrees Celsius, the coldest point physically possible. Kelvin was formidably intelligent, enormously productive, and almost certainly the most authoritative voice in British physics during the second half of the 1800s. In the 1860s, he turned his attention to the age of the Earth. His approach was physically rigorous. He modelled the Earth as a body that had started in a molten state and had been cooling ever since, losing heat to the cold of space from its surface. If you know the thermal conductivity of rock, and you know the current rate at which temperature increases as you go deeper underground, a measurable quantity, the geothermal gradient, you can work backward and estimate how long the planet has been cooling to reach its present state. Kelvin ran the calculation carefully and arrived at an answer that he expressed as a range. The Earth was probably somewhere between 20 million and 100 million years old, with his preferred central estimate settling toward the lower end of that span. This was a problem, a very serious problem for two other branches of science that were, in the same decades, arriving at completely different conclusions about Earth's age. Charles Darwin had published On the Origin of Species in 1859. The theory of evolution by natural selection required an enormous span of time, far more than 100 million years, for the gradual accumulation of the tiny changes that had produced the diversity of life visible in both the living world and the fossil record. Geologists working in the tradition of James Hutton and Charles Lyell, observing sedimentary rock sequences and the slow rates of deposition visible in the present, were similarly pointing toward a very old Earth, one whose age was measured in hundreds of millions of years at minimum. Kelvin found these estimates uncomfortable. He said so repeatedly in lectures and papers, and his authority carried enormous weight. The debate between the physicists' young Earth and the naturalists' old Earth was one of the sharpest intellectual confrontations of the Victorian scientific world. And Kelvin was wrong. Not because his physics was careless, it was not, but because his model was incomplete. He did not know about radioactivity. Could not have known, because radioactivity was not discovered until 1896, when Henri Becquerel found that uranium compounds fogged a photographic plate without any external light source, a spontaneous emission of energy from the atom itself, something entirely outside the framework of classical physics. Marie Curie and Pierre Curie systematized the study of radioactivity in the years immediately following. And it was Ernest Rutherford who grasped the implication that Kelvin had missed. If radioactive elements in the Earth's crust and interior are continuously producing heat, then the cooling model is wrong. The Earth is not simply losing the heat of its birth. It has an internal source, a furnace being continuously stoked, and that stoke had to be added to the calculation. Rutherford delivered a lecture in 1904 at the Royal Institution in London. Kelvin was in the audience, elderly by then, reportedly dozing in the front row. Rutherford, conscious of the awkwardness, framed his point carefully. Kelvin had said that his age calculation would hold unless a new source of heat were discovered. Well, a new source had been discovered. Radioactivity. Kelvin had left the door open, Rutherford noted, and the new physics had walked through it. Whether Kelvin absorbed the remark or simply slept through it, accounts differ. But the physics did not care about the social dynamics of the meeting. Radioactive heat rewrote the Earth's age, and nothing Kelvin had published could stand unchanged against it. The subsequent work of establishing that age precisely is a story of elegant and painstaking chemistry. Once it was understood that radioactive nuclei decay into specific daughter products at fixed rates, the ratio of parent to daughter in a rock sample became a clock. Measure the ratio, know the half-life, calculate the elapsed time. The technique was refined through the first half of the 20th century, and it was applied to increasingly ancient materials, old continental rocks, ancient zircon crystals, and eventually the most primitive materials available, meteorites. The stony debris left over from the formation of the solar system, never processed by the heat and chemistry of a large planetary body, carrying the original isotopic ratios nearly unchanged since the solar system's first moments. Claire Patterson, an American geochemist working at the California Institute of Technology, spent years in the early 1950s developing the analytical chemistry required to measure lead isotopes, the daughter products of uranium and thorium decay, in ancient meteorites with sufficient precision to determine their age. The work was painstaking. Lead contamination from the environment, including the exhaust of leaded gasoline, then in widespread use, was a persistent and maddening problem. Patterson eventually traced it to its source and spent years in a separate famous campaign fighting to have it removed from fuel. But in 1956, having solved the contamination problem in his laboratory, he published his result. The Earth, and by extension the solar system, was approximately 4.54 billion years old. That number came from uranium-238, uranium-235, and thorium-232. From the ratios of the lead isotopes their decay had produced, measured in meteorites that had drifted through space since the solar system's first moments. The same atoms that glow in the mantle and the crust, producing 20 terawatts of heat confirmed by neutrino detectors under mountains, those same atoms, counted differently, as ratios of parent to daughter rather than as particle events in a scintillator, revealed that the planet had been burning for 4.5 billion years. The furnace and the calendar are built from the same bricks. That is not a metaphor. It is a precise statement about nuclear physics and its expression in rock. And all of this, the neutrino detections, the geochemical models, Patterson's meteorite lead, the radiometric ages of the oldest continental rocks, adds up to a portrait of the interior that is, in the circumstances, surprisingly detailed. Because one foundational fact about the exploration of that interior sits beneath everything else. We have never actually been there. Not even remotely close. In the Kola Peninsula of northwestern Russia, in a landscape of boreal forest and tundra not far from the Norwegian border, there is a hole in the ground. It is not particularly wide, roughly 23 centimeters in diameter at its deepest point, barely enough to fit a human arm. But it is, by the measurement of human effort, extraordinarily deep. The Kola Superdeep Borehole was a Soviet scientific project that ran from 1970, when drilling began, until the project was abandoned in 1994. At its deepest, the borehole reached 12 kilometers and 260 meters below the surface. 12.26 kilometers. In the context of everyday distances, that is genuinely impressive, roughly the altitude at which a commercial aircraft cruises, straight down into the solid rock. In the context of the Earth's interior, it is almost nothing. The Earth's radius is approximately 6,371 kilometers. The Kola borehole, the deepest penetration humanity has ever achieved into the planet's crust, reached about 12 kilometers. That is less than 1/5 of 1% of the way to the center. It did not reach the base of the crust. Not even close. Beneath the Russian drilling site, the crust extends to perhaps 35 or 40 kilometers before giving way to the mantle. Kola stopped at roughly a third of the depth of the crust alone, not at the crust-mantle boundary, not anywhere near the 3,000 kilometers of mantle below that, or the 2,500 kilometers of liquid outer core below the mantle, or the final 1,200 kilometers of solid inner core at the center. The drilling stopped, not because the engineers ran out of ambition, but because the rock at that depth was far hotter and under far greater pressure than the models had anticipated. At 12 kilometers down, the temperature had reached roughly 180 degrees Celsius, hot enough that drilling equipment began to behave in ways the engineers had not fully planned for. The rock itself, under the weight of 12 kilometers of overlying material, was almost plastic, not liquid, but no longer the brittle, fractured material encountered in the upper kilometers. Drill bits wore out with disconcerting speed. The borehole had a tendency to close behind the drill as the walls deformed slowly under pressure. The project continued for years against these difficulties, and then it stopped. The deepest hole in the world sits in the Kola Peninsula, capped and quiet now, its mouth a small concrete structure surrounded by overgrown industrial ruins, reading from the outside as nothing more than a closed and rusting door in the middle of a northern forest. We have never touched what is below, and yet we know a great deal about what is there. We know the structure of the mantle. We know that it gives way at approximately 2,890 kilometers to a liquid region, and that this liquid region transitions to a solid center at approximately 5,150 kilometers depth, and that the solid center has a radius of roughly 1,200 kilometers, roughly the size of the Moon. We know the approximate temperatures at the core mantle boundary and at the inner core boundary. We know the density profile of the interior, layer by layer, with enough precision to construct detailed models of its behavior. We know all of this without having drilled past the crust, without having sent any instrument deeper than 12 kilometers. We know it because of seismic waves. An earthquake is, among other things, a probe. When a fault ruptures and releases stored energy, that energy propagates outward through the earth in waves. There are pressure waves that compress and expand the rock as they travel, and shear waves that move the rock sideways, perpendicular to their direction of motion. These waves interact with the material they pass through. They bend when they enter regions of different density, the way light bends when it passes from air into water. They reflect off boundaries between different materials, and one behavior is critical above all others. Shear waves cannot travel through liquid. They require a medium with rigidity, the ability to resist being deformed sideways. Liquids flow instead of resisting. A shear wave arriving at a liquid region simply does not continue. It stops at the boundary. In 1913, a German geophysicist named Benno Gutenberg was analyzing the patterns of seismic waves recorded at stations around the world following earthquakes. He noticed something. At certain distances from the earthquake source, shear waves did not arrive at all. There was a shadow zone, an angular region of the Earth's surface where the shear waves were absent, where the seismographs recorded nothing where something should have been. Gutenberg worked through the geometry carefully. The shadow zone was consistent with a large liquid region at the Earth's center, a region beginning at approximately 2,890 kilometers depth and extending inward. The shear waves could not pass through it. They were blocked by a liquid outer core. Gutenberg had never drilled a meter into the Earth. He had deduced from the pattern of silences in seismograph records that a river of liquid iron lay at the planet's heart nearly 3,000 kilometers below the surface. The boundary he identified carries his name still. 23 years later, a Danish seismologist named Inge Lehrmann added the next layer to the portrait. Lehrmann was analysing records from a large earthquake that had struck near New Zealand in 1929, examining how seismic waves had travelled through the Earth and been recorded at stations across the world. She found something that should not have been there: faint signals arriving in the shadow zone, in the region where, according to Gutenberg's model of an entirely liquid core, nothing should have arrived. Lehrmann worked carefully through the geometry of wave refraction and reflection, and she proposed an explanation. Inside the liquid outer core, there was a solid inner core. Waves that entered the liquid outer core travelled downward, struck a boundary with this interior solid, and reflected or refracted. Those waves emerged on paths that carried them into the shadow zone. That was the source of the mysterious signals. She published her paper in 1936. The paper was single-authored, I, Lehrmann, and its title was The Prime Symbol and the Letter A. Subsequent seismological work confirmed her hypothesis. The solid inner core is real, and it sits there now, roughly 1,200 kilometers in radius, composed primarily of iron and nickel, at temperatures approaching 5,000 to 6,000 degrees Kelvin. Temperatures comparable to the surface of the Sun. And yet, it is solid. Held that way not because it is cool, but because the pressure at those depths, between roughly 330 and 360 gigapascals, raises the melting point of iron above the local temperature. Under the weight of the entire planet above it, iron that would be a glowing gas at the surface is pressed into a solid sphere. Both Gutenberg and Lehrmann built their portraits of the interior from the same raw material, seismic waves from earthquakes, recorded at the surface, their arrival times and amplitudes compared against theoretical predictions, the discrepancies analysed until the geometry of the interior was revealed. It is one of the great indirect measurements in the history of science. The inside of the planet read from the outside, using waves the Earth itself generates, because the Earth is never entirely quiet, and every earthquake is in a sense an experiment performed by the planet on itself. Seismology and neutrino physics converge on the same interior from different directions and with different instruments and different questions. Seismology tells you the structure, where the layers are, how deep, how dense, what their physical state is. Neutrino counting tells you the chemistry, how much uranium and thorium and potassium are dissolving into heat in those layers right now. Neither method requires touching the rock. Both methods treat the Earth as a body that can be read by what passes through it, seismic waves in one case, antineutrinos in the other. The planet is, in this sense, more transparent to human understanding than its surface would suggest. We cannot reach in, but we can listen to what it sends out. The Kola borehole remains capped in its northern forest, having reached 12 kilometers in 24 years of drilling. The Gutenberg discontinuity sits at 2,890 kilometers, discovered in 1913 without a drill at all. Imge-Lehmann's inner core boundary sits at 5,150 kilometers, found in 1936 from a pattern of waves in a seismograph record from New Zealand. And the neutrinos from uranium-238 and thorium-232 pass through all of it, through the inner core, through the outer core, through the 3,000 kilometers of mantle, through the crust, through every meter of the 12 kilometers the Soviet engineers spent 24 years drilling, and continue upward through the air, through the roof of the mountain, through 1,400 meters of Apennine limestone, into the scintillator of Borexino, where very occasionally, once every few weeks, one of them strikes a proton and leaves a double flash that a physicist in a clean underground room records as an event. Each event a vote. Each vote a confirmation. The furnace is real and it is running, and we have found a way to weigh it. There is something quietly staggering about the relationship between what we can reach and what we can know. The deepest our hands have gone is 12 kilometers. Our knowledge extends to 6,371. That gap is not a gap in understanding, it is a gap in touch. We have read the interior from multiple angles, with multiple methods, with enough consistency that the broad outlines are not in serious doubt. We simply cannot go there. We are reading a book written in a language we understand, in a script we can see clearly, stored in a library whose doors do not open and whose shelves we cannot reach. The seismic waves are messengers. The neutrinos are messengers. All of them carry information outward, offered freely by the planet, requiring only that we be patient and clever enough to decode what they bring. What the messages say, assembled into a coherent account, is something like this. The Earth contains radioactive fuel, uranium-238, thorium-232, and potassium-40, with uranium-235 playing a smaller role today than it did in the deep past, when the fast burner was still abundant. This fuel is not distributed evenly through the planet. It is concentrated in the silicate portions, in the mantle, and especially in the continental crust, because uranium and thorium and potassium are lithophile, rock-loving in a precise geochemical sense, meaning that when iron and silicate separated during core formation, these elements remained behind in the silicate material, leaving the iron core with essentially no radiogenic fuel. The heat source is not deep at the center. It is in the body of the planet, and in significant measure in the comparatively thin crust beneath your feet. This fuel is decaying at rates set by nuclear physics alone, rates that do not respond to temperature or pressure or chemical environment, that have been fixed since these nuclei were forged in the deaths of stars before the solar system formed. That will continue at exactly the same pace until, one by one, the remaining nuclei have undergone their transformations. Uranium-238 decays so slowly that half of what was present at Earth's formation remains, and another full 4.5 billion years would have to pass before half of that remainder was gone. Thorium-232 decays more slowly still, at a pace that would require the universe to age to nearly 3 times its current age before reaching its halfway point. These are not fires that will go out suddenly. They are patient beyond any human intuition of patience, beyond any geological or biological timescale, burning at a rate that a human lifetime does not even register as a flicker. The heat they produce, on the order of 20 terawatts, confirmed now by neutrino measurements on 2 continents, adds to the roughly equal amount of primordial heat still slowly leaking out from the planet's violent birth, making a total of somewhere between 44 and 47 terawatts escaping from the surface every second. Spreading thinly across the planet at an average of roughly 87 milliwatts per square meter, quiet and almost imperceptible, dwarfed by the sun's radiation by a factor of 3 to 4,000. And yet this quiet, thin, patient heat is what keeps the planet restless. The story of how it does that, how 20-odd terawatts of radiogenic warmth plus 20-odd terawatts of primordial warmth spread through a mantle of solid rock 3,000 kilometers deep, sets the whole surface of the planet in motion, builds and destroys ocean floors, raises mountain ranges, maintains the magnetic field that surrounds and protects all life, is where the story turns next. But before arriving there, it is worth pausing on what has just been laid out, Kelvin building a careful and physically rigorous model of a cooling Earth, and being wrong because radioactivity had not been discovered yet. Rutherford recognizing in the early 1900s that the hidden heat source changed everything. Patterson spending years fighting lead contamination in his laboratory before arriving. In 1956, at 4.54 billion years, the age written in the lead isotopes of meteorites by the same uranium and thorium whose antineutrinos now stream into detectors under Italian limestone. Gutenberg reading a liquid outer core from a seismic shadow zone without drilling a single meter. Layman reading a solid inner core from a wrongness in that shadow zone, in a single authored paper whose title was 2 characters long. Each of these is a different kind of listening, a different antenna tuned to a different signal from the same inaccessible interior. The planet cannot be excavated on any meaningful timescale. It can only be interrogated from the outside with patience and ingenuity and the willingness to sit with uncertainty for as long as the data requires. Science here does not move fast, because the subject does not move fast. The mantle cools at roughly 100 degrees per billion years. The continents drift at the pace of growing fingernails. A neutrino detector waits months for a handful of events. The pace of learning matches, in some deep way, the pace of the thing being learned. Both are, by any human standard, extraordinarily slow. And in that slowness there is a kind of rest. The furnace has been burning since before the earth had finished becoming round. It burned through the Archean, when the only life was single cells in a shallow ocean and the sky was orange and the continents barely existed. It burned through the Cambrian explosion when something resembling complex animal life appeared in the seas. It burned through the Permian extinction and the Cretaceous and the Ice Ages and the rise of every species that has ever left a fossil. It is burning now, as you listen to this, at a rate that will not change measurably across the whole span of recorded history, past or future. The uranium-238 in the mantle beneath you is decaying this moment at precisely the rate it decayed when the first humans walked the African savanna, and it will decay at precisely that rate when the last human memory has dissolved back into whatever the world becomes after us. There is no urgency here. The planet is patient. The heat is steady. The neutrinos stream upward through the rock and through the floor and through the ceiling and through the air above this building and through the clouds and out into space, by the trillions every second, carrying their quiet message upward from depths no drill has touched and no hand has felt. The earth is not cooling into silence. Not yet. Not for a very long time. And how that patient, steady warmth actually moves the solid rock of the mantle, how it reaches from the depths upward to set the surface plates in motion and keep the magnetic shield alive, is exactly where the story goes next. So let us follow the heat. Not as a flame, not as something violent or sudden, but as the patient, upward pressure of warmth looking for a way out. Imagine the mantle as it truly is, not liquid, not fire, not the roiling lava pit of popular imagination, but something stranger and more improbable than any of those pictures. It is solid rock. You could strike it with a hammer and it would ring. You could chip a piece loose and hold it, cold and heavy, in your hand. And yet, on the timescale of 1,000,000 years rather than a millisecond, it flows. The same property that makes glass technically a very slow liquid, that lets glaciers inch down mountain valleys under their own impossible weight, applies here at an almost incomprehensible scale. The mantle is solid to a seismic wave which passes through in minutes and reads the rock as rigid. But to the relentless, patient push of heat over millions of years, it yields. It bends. It moves. This movement has a name, mantle convection, and the principle behind it is the same one that stirs the soup in a pot on a stove, or curls the smoke above a candle, or causes the visible shimmer above hot pavement on a summer afternoon. Hot material is slightly less dense than cool material. When something is less dense than what surrounds it, it rises. When it rises and reaches a cooler region, it loses some of its heat, becomes denser again, and eventually sinks. Then the cycle begins once more. In a pot of soup, this happens in seconds. In the mantle, a single convective cell, a single slow rotation of rising warm rock and sinking cool rock may take tens to hundreds of millions of years to complete one turn. The heat escaping from the core mantle boundary, and the heat generated continuously in the mantle itself by the decay of uranium-238 and thorium-232 and potassium-40, together provide the energy that keeps this enormous machine turning. Hot plumes of mantle material rise from depth, spreading sideways as they approach the surface, cooling as they go, eventually sinking back down at the edges of the great convective cells. The process is sluggish, almost beyond language. A human life is entirely invisible to it. A civilization is invisible to it. Even the whole of recorded history, 10,000 years of it, is invisible to it. But the rock moves, slowly, steadily, without interruption. The furnace stirs the mantle like a spoon, stirring something so thick you can barely turn it. And this stirring is not idle, it has consequences you can stand on. The rigid outermost shell of the earth, the crust and the topmost sliver of mantle beneath it, together called the lithosphere, does not move as one piece. It is broken into a jigsaw puzzle of enormous fragments, the tectonic plates. There are roughly a dozen major ones and several smaller ones, and they float, if that is the right word, on the more slowly flowing astenosphere beneath. The driving forces are several. One of the largest is called slab pull, when an oceanic plate, which is dense basaltic rock, reaches the edge of a continent and meets a lighter plate, it tips downward and sinks, subducts, into the mantle beneath. As it goes, it pulls the rest of the plate behind it, like a tablecloth sliding off a table when one corner begins to fall. This is slab pull, and it is a powerful engine in its own right. There is also ridge push, the gentle outward pressure from the mid-ocean ridges where new seafloor is constantly being borne from mantle material, rising to fill the gap as the plates spread apart. All of it, the slab pull, the ridge push, the deep mantle currents that help organize where the plates go and how fast, traces back to the heat. The heat is the original source of motion. Without the furnace below, the plates would not move. The continents would stop. The ocean floor would stop being recycled and renewed. The whole restless surface of the earth, with its mountains and trenches and earthquakes and volcanoes, would gradually quiet. The rate of movement is sometimes described this way, about as fast as your fingernails grow. A few centimeters a year. Stand on the European plate and the North American plate, and you are moving apart from each other right now at a pace you cannot feel and cannot see, but which, across 100 million years, opens an ocean between you. The Atlantic is the scar of that slow parting. The Himalayas are the crumple zone where the Indian plate, riding the deep conveyor, pressed northward into Asia and pushed the rock upward. None of it is fast, none of it is sudden, except at the moments when stress accumulated over centuries releases in an instant along a fault. The motion itself is as patient as the furnace that drives it. There is something worth pausing on here before we go deeper. The heat is escaping the earth. The mantle convection is the mechanism by which warmth born in the planet's interior finds its way outward, dissipating gradually into the rock above and eventually into the ocean floor and the continental surface. Plate tectonics is part of that cooling system. The mid-ocean ridges, where hot mantle wells up and makes new seafloor, are vents, in a way, places where the deep heat has found a path upward. The subducting slabs carry cold surface rock back down into the mantle, cooling it from the other direction. The whole plate system is, among other things, a heat exchange mechanism of planetary scale, a way for the furnace's warmth to move through the rock and ultimately escape. And yet the furnace keeps replenishing what is lost, because uranium and thorium are still decaying in the rock, every second, every hour, every million years, at a rate that has barely changed since before the dinosaurs existed. The system is not in balance. The Earth is cooling. Slowly, but it is in a kind of long equilibrium. The input from radioactive decay and the slowly diminishing reservoir of primordial birth heat together nearly match the output flowing outward to the surface. The result is a planet that has remained geologically active across the entirety of its history so far, which is a less common situation in the solar system than it might seem. But the story of what the heat does is not finished with the mantle and the plates. Because beneath the mantle, below the core mantle boundary, at a depth of roughly 2,890 kilometers, there is something else entirely. The outer core is liquid. Not lava, not magma. Those are silicate rock in a molten state, and they belong to the mantle world above. The outer core is liquid iron, alloyed with nickel and some lighter elements, whose exact identity is still being debated, at temperatures somewhere between 4,000 and 6,000 degrees Kelvin. At those temperatures, the iron is genuinely fluid in the ordinary sense of the word. You could pour it, if you could somehow contain it, which you could not. Because every material you could use to make a container would itself be vaporized or dissolved. This is not a metaphor or an approximation. The outer core is a vast ocean of liquid metal enclosing the solid inner core below, itself enclosed by the solid mantle above. And within that liquid iron ocean, something extraordinary is happening. The liquid iron is moving. It is convecting, just as the mantle convects, but in a different way and for overlapping reasons. Some of the convection is driven by heat. The core is losing heat outward through the core mantle boundary, which causes cooler, denser iron to sink and warmer iron to rise, just as in the mantle above. But there is a second driver, and in some models it may be the more important one. As the Earth slowly cools over billions of years, the boundary between the liquid outer core and the solid inner core, the inner core boundary, at a depth of roughly 5,150 kilometers, is very gradually moving outward. The inner core is growing. It is freezing, extremely slowly, at enormous pressure. Iron is crystallizing at the inner core boundary and adding to the solid mass of the inner core beneath. When iron freezes out of the alloy, it leaves behind the lighter elements, sulfur, oxygen, silicon, whichever of them are dissolved in the liquid iron, and the exact mixture is still a matter of active research. Those lighter elements are expelled upward into the liquid outer core, making the remaining liquid near the inner core boundary lighter, which causes it to rise. This is compositional convection, motion driven not by temperature differences, but by differences in composition, in the density of the fluid. The latent heat released by the freezing, the heat that iron gives up as it transitions from liquid to solid, the same process that releases warmth when water freezes into ice on a winter night, also adds to the energy budget of the outer core. Together, thermal convection and compositional convection keep the liquid iron churning. That churning liquid iron, electrically conducting and moving at the speeds of a geophysical fluid, generates a magnetic field. This is the geodynamo. The principle is not deeply mysterious. A moving electrical conductor in the presence of a magnetic field generates electrical currents, and electrical currents generate magnetic fields of their own. And those fields can reinforce and sustain the original field, and the whole self-sustaining system is called a dynamo. What is remarkable is the scale. The outer core, this liquid iron ocean, is itself several times larger in radius than the Moon. The convective motions within it are complex and three-dimensional, organized partly by the Earth's rotation into columnar structures aligned with the planet's spin axis. The resulting magnetic field is large enough to extend out into space well beyond the surface of the planet, forming the magnetosphere. The temperatures at the inner core boundary, where iron is slowly freezing at pressures of somewhere between 330 and 360 gigapascals, pressures so extreme that the number has to be held in the mind abstractly, because no everyday experience maps onto them, are estimated to be somewhere around 5,000 to 6,000 Kelvin. 5,000 to 6,000 degrees on the absolute temperature scale. The surface of the Sun, the photosphere, the visible bright disk that you cannot safely look at, sits at about 5,772 Kelvin. The center of the Earth is comparable in temperature to the surface of the Sun. Not because anything is burning there, not because any flame exists, but because of pressure and the slow leak of primordial heat from 4.5 billion years of compression. The solid inner core is hotter than the Sun's surface, and yet it is solid, because at those pressures the melting point of iron is higher still. Temperature and pressure together decide what state matter takes, and down there the pressure wins. The inner core itself is roughly the size of the Moon. That is one of those facts that settles into the mind slowly. Hidden at the center of the world, deeper than any drill has gone or ever will go, is a ball of solid iron the approximate diameter of our nearest neighbor in space. Sitting in a sea of liquid iron, at temperatures the surface of the Sun would recognize. And it is growing, almost imperceptibly slowly, one crystallized iron layer at a time, releasing latent heat and expelling light elements as it does, feeding the dynamo that shields everything above it. Think about that shield for a moment, because it is easy to take for granted. The Sun continuously streams charged particles outward in all directions. This is the solar wind, a flow of electrons and protons and heavier ions expanding from the corona at hundreds of kilometers per second, reaching the Earth and every planet in the solar system in a matter of days. Without any protection, the solar wind would interact directly with the upper atmosphere, stripping away light gases over time and eroding the conditions that allow water to remain liquid on the surface. Over billions of years, without a magnetic shield, an atmosphere like Earth's would be considerably more vulnerable to this loss. The magnetosphere, the vast bubble of magnetic influence generated by the geodynamo, deflects most of this flow. The charged particles from the solar wind curve around the Earth's magnetic field lines, funneled toward the poles where they produce the aurora, but largely turned aside before they can interact with the atmosphere in damaging ways. The shield is not perfect, some particles get through, and the outer radiation belts contain trapped particles that are themselves a hazard for satellites and astronauts. But the magnetosphere is the reason the Earth's atmosphere has survived largely intact for 4.5 billion years. The furnace powers the dynamo. The dynamo powers the shield. The shield protects the atmosphere. The atmosphere protects the surface. The surface is where you are. The chain from the decaying uranium and thorium in the mantle rock to the conditions that allow you to breathe is real, and it is not metaphorical. It is causal, one link following from the previous one, all the way from the nucleus of a uranium-238 atom, completing one step in its billion-year decay sequence, to the air above your head remaining thick enough to scatter sunlight blue. And then there is Mars. Mars is roughly half the radius of Earth, 3,390 kilometers, compared to Earth's 6,371. In terms of mass, Mars is about 11% of Earth's mass, a much smaller world. And that difference in size, that seemingly simple geometric fact, led to a very different fate. Here is the principle. The amount of heat a planet generates from radioactive decay, from residual birth heat, scales roughly with its volume, which grows as the cube of the radius. But the rate at which it loses heat to space scales with its surface area, which grows as the square of the radius. A smaller planet has a larger ratio of surface area to volume. It loses heat faster relative to how much it generates. It cools quicker. The physics is the same for a hot loaf of bread and a hot planet. The small loaf cools faster than the large one, because the surface through which heat escapes is large relative to the volume that holds the warmth. Mars ran a higher surface-to-volume ratio than Earth, and it ran it for 4.5 billion years. The result was a planet that shed its heat faster. The mantle convection slowed. The tectonic activity, if Mars ever had plate tectonics in the way Earth does, which is still debated, diminished. And the dynamo in the liquid outer core, dependent on a sufficient heat flow from the core and sufficient convective energy to sustain itself, eventually ran down. Mars once had a global magnetic field. This is not speculation. When spacecraft from the Mars Global Surveyor mission carried a magnetometer over the ancient southern highlands of Mars in the late 1990s, instruments built by Mario Acua and his colleagues found strong magnetic signals frozen into the rock. Ancient basalts, formed billions of years ago when Mars still had a magnetic field, had cooled and locked in the orientation of that field, preserving it as remnant magnetization. The same process by which Earth's seafloor stripes record millions of years of magnetic reversals. The record is there in the Martian highlands. Mars had its dynamo. Mars had its magnetic field. At some point roughly 4 billion years ago, the dynamo shut down. The field collapsed, and Mars has been magnetically quiet ever since. The consequences were not immediate and dramatic. They played out over hundreds of millions of years. But without its magnetic shield, Mars became progressively more vulnerable to the solar wind. The MAVEN spacecraft, the Mars Atmosphere and Volatile Evolution mission, launched in 2013 and arriving at Mars in 2014, measured this process directly. Bruce Jakosky and his colleagues found that the solar wind is stripping gas from the Martian atmosphere even now, at a rate that becomes significant over geological time. Over billions of years, the accumulated loss has been enormous. The thick atmosphere that Mars may once have had, warm enough to allow liquid water on the surface, was gradually thinned by the relentless erosion of the solar wind. The pressure dropped below the point where liquid water can exist on the surface. Temperatures fell. The rivers and the lakes and whatever potential they held dried out. Mars became the cold, thin-aired, frozen desert it is today. NASA's InSight lander, which touched down on Mars in 2018 and operated until late 2022, listened for Martian earthquakes, Marsquakes, using a seismometer called SEIS that was sensitive enough to detect the planet's deep interior. InSight confirmed that Mars still has a core, and that core is at least partly liquid. But the planet's interior is far quieter, far less dynamic than Earth's. No plate tectonics churns the Martian surface. No vigorous convection stirs the mantle with anything like the energy that moves Earth's plates. The furnace that once gave Mars its dynamo and its magnetic shield has not gone entirely cold, but it has dimmed enough that the dynamo could not sustain itself, and the surface above has been left to the mercy of space. Mars is the cautionary twin. It had the same origin story as Earth. Both worlds formed from the same rotating disk of gas and dust around the young sun. Both accumulated the same rock-forming elements, including uranium and thorium. Both were battered by the same late bombardment of asteroids. Both may have had liquid water and active geology in their early histories. The difference was size. 11% of Earth's mass. That was the margin. That was what separated a world that stayed alive and geologically restless, that kept its dynamo running and its atmosphere intact, and eventually allowed something to evolve and build radio telescopes, from a world that went cold and still and silent at the surface, its history frozen into its rocks. Its magnetic memory preserved only in the ancient highlands as a kind of epitaph. The moon shows the same pattern. Small worlds cool fast. Geological death comes to the little ones first. Earth, in this sense, was lucky in its size, lucky to be large enough that its surface-to-volume ratio kept the heat escaping slowly, that the mantle convection had enough energy to sustain itself across billions of years, that the core had enough heat flow to keep the geodynamo running. Lucky, if that is the word, that uranium and thorium happened to be present in the right abundances, concentrated in the mantle and crust by their lithophile chemistry, providing a continuous resupply of energy that has stretched the active life of the planet far beyond what pure primordial heat alone would have sustained. And that primordial heat, the other half of the budget, is itself a story worth returning to, now that we can see what it was buying. The birth of the Earth was not a quiet event. For perhaps the first 50 to 100 million years of the solar system's existence, the region where Earth now orbits was a war zone of colliding rock. Planetesimals, the early solid bodies that preceded the planets, ranging from pebbles to bodies the size of small moons, were circling the young sun in their billions, crossing each other's orbits, colliding, sometimes shattering. sometimes sticking, slowly but chaotically, building larger and larger bodies through a process called accretion. Each collision converted kinetic energy into heat. A body the size of a small asteroid, striking the growing proto-Earth, would release the energy of thousands of nuclear weapons in a fraction of a second, and this happened not once, but billions and billions of times. The heat accumulated faster than it could escape. The proto-Earth grew molten. Then, at some point, while this violent accretion was still ongoing, perhaps 40 to 100 million years after the solar system formed, something happened that geoscientists call the iron catastrophe. Though it was not a catastrophe in any human sense, but simply a phase transition of planetary scale. As the interior of the growing Earth became hot enough for iron to melt, the dense liquid iron, far heavier than the silicate rock around it, began to sink. Rain downward through the mantle rock is perhaps the closest analogy, though the scale makes every analogy awkward. Blobs of liquid iron, themselves perhaps as large as small hills or mountains, sinking through rock that was yielding under the heat and pressure. As that iron fell toward the center, it released gravitational potential energy. The descent of iron from the surface and mantle to the core is estimated to have raised the temperature of the whole Earth by something like 1,000 to 2,000 Kelvin. 1 or 2,000 degrees of heating across the whole planet from gravity alone. The Earth was effectively recharged by the act of differentiating, by sorting itself into a dense iron core and a silicate mantle and crust. The iron catastrophe left the young Earth with a core and set the stage for the geodynamo we still benefit from. And somewhere in that same violent early period, a body the size of a small planet struck the proto-Earth in a collision so energetic that it blew off an enormous amount of material into orbit. Some of that material accreted to form the Moon. The rest settled back. This event, the giant impact, hypothetically caused by a body often called Theia, would have left the Earth largely or entirely molten, a magma ocean covering the whole surface, kilometers deep, glowing, a world that from space would have looked like a dim star. Much of the primordial heat that the Earth carries today is the slow cooling of that magma ocean, the gradual leak of birth energy accumulated over those first terrible millions of years. The magma ocean solidified, the crust formed, the mantle began its long cooling, its convective churning, its patient million-year cycles of rising and sinking. That was 4.5 billion years ago. And here you are now. The warmth that began in the violence of accretion and core formation and the Theia impact is still here, still slowly leaking outward, still contributing its fraction of those 44 to 47 trillion watts flowing through the surface of the planet every year. It is the same birth heat, dimmed but unextinguished, that has been travelling outward through the rock since before the Moon was formed, since before the oceans condensed from the steam of that early world, since before any life existed to wonder at any of it, and alongside it, every second, the uranium and thorium and potassium in the mantle and the continental crust are still decaying, still releasing their tiny individual packets of energy, still generating their geoneutrinos and sending them streaming upward through the rock and through the floor and through you by the trillions in every direction upward into space. The furnace is still lit. It is not the same furnace it was 4 billion years ago. It is quieter now, slower, because the short-lived isotopes like uranium-235 and the long-extinct aluminum-26 have largely burned down. But it is the same fire, the same physical process, slower and more patient, and no less real. The Earth is cooling. This is true, and worth sitting with. The mantle has been losing perhaps 50 to 100 degrees Celsius per billion years on average, a pace so slow that across all of recorded human history it has changed by a fraction of a degree, imperceptible in any observation, immeasurable on any human timescale. Over billions of years into the future, the cooling will eventually matter. The mantle will become more viscous as it cools, the convection will slow and reorganize, and at some point, perhaps in 5 billion years, perhaps more, the models differ. The combination of slowing mantle convection and diminishing heat flow from the core will weaken the geodynamo. Earth will move towards something resembling what Mars became, though far more slowly and far in the future. Not alarm, not drama, not even something worth calling a countdown. Just the long, patient trajectory of a cooling world, still billions of years from its end. For now, the furnace keeps burning. For now, the mantle flows. The plates drift. The continents ride their invisible currents at the pace of fingernails and think of themselves as permanent. The liquid iron in the outer core churns under the immense pressure and generates its magnetic field, the invisible structure that deflects the solar wind and keeps the atmosphere whole. The neutrinos stream upward by the trillion through the ground you sleep on, carrying their message from the deep earth, their tiny energies, the signature of uranium and thorium still decaying in the mantle rock below. Deep in the ocean, at the mid-ocean ridges where the plates spread apart and mantle material wells up from below, the water of the deep sea warms slightly against the new basalt. Chimneys of superheated water, the hydrothermal vents called black smokers, rise from the seafloor where the furnace finds a crack to breathe through. And around those chimneys, in complete darkness, in water hot enough to cook, ecosystems thrive, tube worms and crabs and microbes that have never seen sunlight, that need none, that run entirely on chemistry, on the chemical energy released when the hot mineral-rich water meets the cold seawater above. Life in those vents owes nothing to the star 93 million miles away. It owes everything to the furnace below. And there is something quietly staggering in that, if you let yourself feel it. We tend to think of the sun as the source. The sun warms us, the sun drives the weather, the sun powers the food chain, the sun is the reason the surface is alive. All of that is true. But somewhere on this planet, right now, in the absolute darkness at the bottom of the ocean, something is eating the heat of the earth itself. Something found a way to live on the buried furnace, independent of the star. The food chain there begins not with photosynthesis, but with chemosynthesis, the conversion of chemical energy from the hot mineral water into biological energy, one step removed from the heat of the mantle, one step removed from the decay of uranium and thorium in the rock below. Life did not wait for sunlight. It found the furnace. What keeps the planet restless is not one thing. It is a budget, a ledger, two columns that together add up to the world as it is. On one side, the birth heat, the gravitational energy of accretion, the heat of differentiation, the enormous thermal pulse left by the iron catastrophe and the Theia impact, still slowly leaking outward through the mantle over geological time, billions of years after the collision that made the moon. On the other side, the ongoing decay, uranium-238, thorium-232, potassium-40, and in the deep past uranium-235 and the extinct aluminum-26, releasing energy in their nuclei at rates set by their half-lives. Rates that will not change regardless of temperature or pressure or chemistry, rates that are as close to absolute as physics offers. Together, these two sources produce something in the range of 44 to 47 trillion watts. Together, they feed the convection of the mantle and the convection of the outer core. Together, they keep the plates moving and the dynamo running and the magnetic shield intact. Together, they are the reason Earth is not Mars. And we know this, we can actually know this, not by guessing, not by inference from rock samples alone, but by catching the ghost particles, because deep under a mountain in Japan and deep under the rock of central Italy, in tanks filled with liquid scintillator and lined with photomultiplier tubes and shielded by hundreds of meters of rock from the noise of the cosmic rays above, physicists sat for years and counted. They counted the geoneutrinos, a dozen events in a year, sometimes fewer, each one a tiny double flash, positron and neutron appearing in sequence inside the detector, the unmistakable signature of an anti-neutrino that had travelled upward from the mantle through thousands of kilometres of rock without being stopped by any of it, and had finally collided with a single proton in the liquid and left its mark. Camland in Kamioka counted them first, in 2005. Borexino at Gran Sasso counted them independently, refining the measurement across the 2010s and into 2020. The two detectors, on opposite sides of the world, looking up through different thicknesses of different rock, agreed. The radiogenic heat is approximately 20 terawatts, about half the total. The model prediction, made from bulk silicate earth chemistry and half-life tables, was confirmed by direct particle counting. The scale that physicists built under the mountains is not a metaphor, it is a real measurement of a real mass of radioactive fuel in the real interior of the real Earth. We have never touched the furnace. The deepest hole we have ever drilled, the Kola superdeep borehole in Russia, reached 12 kilometers and change before heat and pressure defeated the drill, leaving it less than 0.1% of the way to the center, not even through the crust. We read the interior with seismic waves. With the shadow zones that Benno Gutenberg mapped in 1913 to reveal the liquid outer core, with the reflected signals that Inge Lehmann noticed in 1936 and followed until she found the solid inner core inside it. We read it with the decay clocks themselves, the same isotopes that heat the Earth having given us its age, Claire Patterson's measurement from meteorite lead in 1956, 4,540,000,000 years. We read it now with the neutrinos, those nearly massless messengers that the furnace sends upward by the trillion every second, and that we catch, one per week or so, in the underground tanks we built to listen. The Earth keeps its furnace buried. It does not announce it. There is no glow visible from space, no signature in the infrared that would let an alien astronomer know, from a distance, that this planet has a self-sustaining heat engine inside it. The heat flux at the surface, that 87 to 92 milliwatts per square meter, is too small to be distinguished against the sunlight it sits under. The planet holds its warmth quietly, patiently, invisibly, letting it out only in the slow movement of the plates and the invisible field lines of the magnetosphere and the occasional fire of a volcano above a hot spot. The furnace is not a spectacle. It is a condition. It is the background state that everything else depends on. Uranium-238 will have a half-life of 4.47 billion years, whether or not anyone measures it. Thorium-232 will take 14 billion years to exhaust half its store, whether or not any detector is ever pointed at its signal. These clocks do not know they are being watched. They do not know there is anything to watch. They decay because nuclei decay, because the strong force and the weak force balance as they do, because the particular arrangement of protons and neutrons in those specific atoms is not quite stable, and so over vast stretches of time they rearrange themselves into something that is. The heat is a byproduct. The geoneutrinos are a byproduct. The convecting mantle and the drifting plates and the geodynamo and the magnetic shield and the thick blue atmosphere and the liquid water and the deep sea vents and the creatures that live there. All of this is downstream of a nuclear process in a rock that has never been seen and never will be seen, happening in the dark, in the heat and pressure of the deep earth, at a rate that barely changes across a human lifetime or a civilization or even an epoch. Sit with that for a moment, if you can. Not as an abstraction, as the actual situation. The rock beneath this building is right now releasing heat that was stored there before your country existed, before any country existed, before the species existed. It is releasing it slowly, steadily, in the way that thorium and uranium release it, one decay event at a time, one nucleus at a time, each event releasing a burst of energy small beyond measurement. Each burst warming the rock by a fraction no thermometer could detect, the accumulation of billions upon billions of such events over billions of years, building to the 44 trillion watts that keep the surface alive. The planet is patient in a way that makes the word patient feel inadequate. It is not patient in the way a person is patient, waiting for something to happen. It is patient in the way that physics is patient, without effort, without intention, without urgency, simply running at the rate it runs, maintaining the conditions it maintains, doing what it does. And those conditions include you. They include the atmosphere you breathe, thick enough because the magnetic shield has preserved it across billions of years of solar wind. They include the moderate climate, stabilized in part by the geological carbon cycle, itself driven by the plate tectonics that the buried heat runs. They include the water in the oceans, still here in liquid form, because the surface temperature falls within the window where water is a liquid and not ice or steam, a window that requires an atmosphere, which requires a shield, which requires a dynamo, which requires a heat engine, which requires uranium and thorium still decaying in the mantle rock beneath your feet. You are not separate from the furnace. You are an outcome of it. One of the outcomes among many possible ones on a world that happened to be large enough to keep its heat, that happened to have the right abundance of heat producing isotopes. That happened to form where it formed, and that has been running its buried engine with a kind of absolute reliability for 4.5 billion years without interruption or pause. Mars never made it this far. Mars had its chance, and the geometry of its smaller body meant it ran out of time before life, if life ever started there at all, had long enough to do what life did here. We carry, in our exploration of Mars, a quiet understanding of what we are looking at. Not just a dead world, a world that ran its furnace for a while and then let it go too quiet to sustain the conditions that might have let something like us happen there. The InSight seismometer, listening to the faint trembling of the Martian interior. The MAVEN instruments, measuring the thin atoms of atmosphere escaping at the top, the ancient remnant magnetism frozen in the highland rocks. These are the records of a furnace that burned and dimmed and left its planet at the mercy of space. This planet has not dimmed, not yet. It is cooling. It will always be cooling. The primordial heat is finite. And even thorium's 14 billion-year clock will reach its halfway point eventually, but for now, in the present geological moment, the furnace burns at a rate that has changed by only a small fraction across all of human history. That will change by only a small fraction across all of human history still to come. The planet is patient. The decay rates are fixed. The heat will keep flowing outward through the rock for longer than the sun will remain as it is today. That is not a small thing to know. That physicists built tanks under mountains and waited for the ghost particles and counted a few dozen of them over years of watching, and from that counting confirmed a budget that explains why the surface of the Earth is alive. That is one of the more quietly remarkable facts about what this species has managed to learn in the time it has been here. The furnace beneath you is not dramatic. It does not announce itself. It hums along, in the dark, in the heat and pressure of depths no instrument has ever directly visited, generating its trillion neutrinos per square centimetre per second, keeping the mantle in its slow convective flow, keeping the outer core in its churning liquid motion, keeping the dynamo that keeps the field that keeps the air. It has been doing this since before the moon was fully formed. It will be doing this long after any record of this night has dissolved. Rest, and the rock will still be warm beneath you. Rest, and the continents will still be drifting their few centimetres toward wherever they are going. Rest, and a trillion ghost particles will still be passing through you, upward from the deep earth, carrying their quiet signal from the nuclei of atoms that have been slowly rearranging themselves since before the first sunrise ever lit an ocean. That is what keeps the planet restless. A dual budget, half ancient and half ongoing, verified by particle physics and geology and 4 billion years of continuing evidence at the surface. The buried furnace is real, it is measurable, and it is still burning. Not urgently, not dramatically. With the absolute patience of deep time, which is the only kind of patience the Earth has ever known. If something in tonight's script made the Earth feel different to you than it did before, larger underneath, or older, or quieter in the way that very deep things are quiet, leave a thought in the comments. Something small is fine. The Earth doesn't require much. It just keeps going. History will still be here in the morning. For now, rest.